All right, we are back with the code book. Um, Hopefully we can finish it up soon. Yeah, so we're on section P. We've done T, I, A, G, H, and F. We just have P, which is phase estimation, and S, which is shores left to go. And then I can finally do something else besides this. I have some ideas, but none of them are quite as easy as these. So yeah, let's get started with this. Phase, all right. Look at that, that's just a number. Phase is a number. Maybe all reality is a number. That's a metaphysical position for you right there. And this will estimate the phase because, right, this is the principle of phase kickback. This is a superposition. This makes the global phase, right here's a global phase, into a local phase because it's now only relative to the one part of the qubit somewhere over here. I bet it. Yeah, see, because it only applies it here, it makes the global phase a local phase, which is then measurable. For example, if this is -1, right, this will collapse to state 1. There's just an example. All right, you're given a unitary that is promised to be either the z-gate or the negative z-gate, where the negative z-gate is the same as the z-gate, just with negative eigenvalues, but it doesn't matter because the eigenvalues are plus or minus 1, so anyway, write a quantum program using phase kickback that will result in the state 0 with a probability of 100% on the first qubit if z is applied in a probe. Okay, so what we want to do is we want to say, let me actually bring a quick calculator so I don't mess up this this math. So I go to e to the 2, I cannot type I, this is 1. And if I do e pi to the negative, this will be -1. No, that's also 1. Okay, what am I doing here? Okay, so, well, let's do the first thing that we definitely know. We definitely want QML dot Eigenvector is equal to 0. We definitely want QML dot Eigenvector is equal to 0. Now, QML dot, I don't know, I don't remember these control unitary, is that what it is? Let's see. I guess it might be parametric. Oh, controlled qubit unitary. Here we go. Controlled qubit unitary. U is unitary. Wires. Let's look at an example. Control wires. Wires equals 0. One. All right. Oh, does QML.props take as something in? Is there a way I can just get the first 2 qubits? Oh yeah, I can just do wires equals 0. All right, there we go. Would you look at that? Now, if we wanted to try with this 8, oh right, I can't change it. Okay, well. Look at that. Look at that. Find the eigenvalues of the x gate. Prepare an eigenvector of x as an input to the target wire. Apply the phase kickback circuit. Obtain the probabilities on the control wire. Okay. So the first thing we can do is prepare an eigenvector. How do I prepare? I forget if I want to. I don't understand. Oh, plus. Oh, I guess we can just do it the easy way. If eigenvector plus, then we want to do the poly X, I always forget. Actually, you know, here's some quick coding efficiency techniques I can do right here. Look at this, saving so many lines of code. Look at that efficiency right there. That's good. All right, now we want to do our phase kickback circuit, which is the human.animal on 0, control 1, there we go. I misspelled one of these. There we go. Enter the correct values. Oh, well, I know that's one and negative. Actually, I don't know if those are normalized. Oh yeah, wait, that's ridiculous. I don't know if 1 is normalized. That's funny. I'm funny. Okay. All right. This is going along nicely. I'm prepared. I know the last 2 videos, I think, I've encountered some very difficult challenges that were very annoying, but thankfully my obscene amount of Elden Ring playtime has now prepared me for banging my head against the wall for many hours. Also, there's a rendering error right here. It looks like, yeah, looks like they have they forgot a left $sign over here to put it into equation mode, I guess. It's probably what it is. Looks like they also forgot a... Oh, no, never mind. Oh, they actually use L-vert. I just actually used a little upper. I don't know. I don't know what that's called, the L-vert key. Okay, yeah. Yeah, I think they just forgot something there. But anyway, moving right along. Wow, look at that. Look at that circuit right here, phase estimation right here. Wow. Computes u at the power of u to the 2 to the k. All right. Given a, oh, no. I was going to do a for loop, but I guess there's a matrix power, which is pretty handy. Then now it's not matrix power. Okay, wow. I was gonna do a for loop, but I did not know that existed. Okay, so what we want to do is return numpy.len out.matrix power unitary 2 to the k. All right, would you look at that? Wow, we're on a roll. They really should have implemented better printing. They should have like a custom print function for that, because that's not a pretty way to look at a matrix. Implement a subroutine that applies u to the 2k unitaries on the target wires controlled on the estimation wires. Want a function that applies a sequence of powers. Okay, so first what we want to do is unitary equals target u equals u power 2k. I'll just do u is equal u power 2k of u comma unitary comma I, right? Because we want to generate these specific unitaries. ui for I in range length of estimation matters. All right, now that we have that, what we want to do is we want to say for I in estimation wires. We would now like to do a, I should do actually I for estimation. We will do controlled qubit unitary. The unitary is us of I. Control, what it is, control wires. Wires equals estimation wires of I. I'll make a new one. And the wires equals target. There we go. That should work. Let me double check. But what we actually want is first. There we go. Implement the quantum phase estimation subroutine given a unitary set of estimation wires. Okay. So what we want to do is Hadamard. We already have this section here, inverse quantum Fourier transform. All right, so we want to do for I in estimation wires with Hadamard equals I. Now we want to call our apply control powers of u unitary, and now a, and now we want to do the dot t. Somewhere on here is a. Okay, this is why the docs are so annoying, is because I can't just QFT. How do I do inverse? Really? There's no inverse QFT? Why? Why? All right. Let's see. Dot QFT dot add thing. See if this works. All right. All right. Wires equals. I really have to do. Oh, and it's not right. All right. Oh, I need to actually do prepare eigenvector. Oopsies. Oopsies, forgot prepare eigenvector. There we go. What do you know? Can we call the QPE function again? Oh wait. Estimate the value of phase. Estimate the value of a phase measurement given the probabilities on the estimation wires. Estimate the phase associated with the T gate when the eigenvector is prepared in the state 1. Okay, so this is to the first, to the second. Okay, so what we want to do is these equals array then we want to do learn some values. No, is it the probabilities are no, okay. I don't know if the probability, let me print them. Let's see. Yeah, what we actually want to see is increment was 2 to the third. 8. We want to increase okay, it is something going on. Let me check. Let me look at this. Should be 1/8. 1/8 is 1 point. Okay, I'm literally getting it right. Output should be a floating point. Okay, well, what the hell is this type then? Oh, it's okay. Really have to cast this to a float. That's funny. That's really funny. There already is a QPE template. Unitary target wires, estimation wires. Unitary target. Bonds. Wires. Nice. All right, we are going through this. All right, what's going on over here? Using the QPE algorithm, estimate the two most likely outcomes of the phase of the eigenvector 1 of a unitary operator. There has got to be a better way to do this. I am very positive that there's got to be. You have a flag for me to fill out. That's funny. Okay, so what do we have here? Actually, let me copy this. This was a handy little thing that I did before. Okay. All right. Bound 1 equals 1 arg. Probs. All right, there we go. Tensor. Okay, well, we'll cast it to a list then. Oopsies. Why is this a tensor? How do I convert this out of tensor units? I don't want it to be a tensor anymore. What? Oh. So I just do this. There we go. Okay, now I'm just trying to fix this. I realize there's a problem before. All right, there we There we go. This should be better. The lower and upper bound of the phase. It should work. What's going on here? All right, the maximum 0.01, 0.9 right here. 0.02. Yeah, I don't understand why this is wrong. Well, let's try. Okay, that was a mistake to print that out. Oh, maybe I have to make sure that upper bound 1 is lower and upper bound. Yeah, I see. I should probably make sure that this is return. There we go. Okay. Huh. Okay. Okay, well, that doesn't make sense that that's the lower bound. I think this should be the lower bound of estimate. Like, this is lower certainty. This is a higher value. The lower bound. This is the lower bound, right? The 0 is the lower bound. So what we want is okay, let me not print this anymore. Let's try with a bigger circuit. Okay, there we go. Let's try with 9. All right, we got it working. It was just a little confusion. Okay. Given a unitary, return its list of phase. What am I supposed to? Okay. On a device with 10 qubits, the last wire is set. Estimation. Calculate the phase estimation starting at 1, 2. Okay, so we want to see how it changes with the change in estimation wires. All right. Is this what they want? I don't know if phase window does. To be honest. So I'm not going to use it because I don't understand what it does, because there's zero information given on phase window. So that's very not helpful. All right, let's do that. That's under. What is this supposed to be? I don't understand. Oh, a list of phase windows. Oh, maybe this does make sense then. Oh, I see. I bet this is what they want. What is this even? What am I even looking at right now? What are these blue lines? Bound 1, bound 2. Okay. Well, it does label which is which, but I guess it doesn't matter. A mixed bag. All right, so let's see if we can do this. We're at 32 minutes. Can we blitz out the last section? Do I risk it? Yes, absolutely. Let's go for it. The objective of this coder size. Wow, that's a nice lingo. Prepare to target wires in superposition of the eigenvectors of the T-gate. Oh, thank God it does that for us. Oh, let's test this out. Wow. What am I supposed to be doing right now? Oh, oopsies. But it's going to be half and half. Wow. Okay. Fun. All right. And this exercise, we'll be looking at 2-qubit unitary to control Z gate. Modify the values of alpha, beta, gamma, and delta to observe the. Okay, let's check this out. All there. All there. Now let's try. Wow. Look at that. Probability of 0 is 0.75. There is no function done. Oh, please change the return value of the function done to a probability value. No, is it supposed to be? What is going on right now? Modify the values of alpha, beta to observe the changes When you're done testing out, change the value of to return the probability of observing the state 1, 0, 0. Okay, I'm very not paying attention. There we go. My bad. I was not paying attention. Okay. In this exercise, we will look into unitaries that have more than 2 eigenvalues and eigenphases who cannot be represented with exactly 4 bits. Prepare the target wires with equal superposition. Okay. 1/4, 1/4, 1/4, and 1/4. Done. Find one of the phases of the QML.CRX with rotation angle. Okay, CRX. Okay. With rotation angle 1/3. 0, 1/3. Okay. Modify the value of mystery phase to the phase with the second largest probability. Mystery phase is is this supposed to be the phase or the probability? Phase value. Phase value is, how many are these? 1, 2, 3, 4. 2 to the -4th times just 1, right? Oh no. 2 to the -4th times. What is it? Oh. I don't remember what this is. I plus I equals I. There we go. All right, was not a lot of coding, so okay, I'm not done. What's going on? Okay, not again. Oh, why does this keep happening? Okay, well, hold on 1 second. I will. Okay, I just had to clear the cache, but that of course wiped out our progress, but that's and the number of times I've had to do that. It'd be so sad if I was not. Oh, there's a form to fill out. Okay, well, I will fill this out. I will actually provide good information when I finish the code book. All right, Shor's algorithm, 5 parts. We will do that next time. For now, I have procrastinated on homework long enough.